Good day, welcome to this week's lesson. This week we continue with the introduction to the principles of GIS. So last lesson we were talking about the various components that make up a geographic information systems. We talked about hardware, software, data, people. Network here refers to that connectivity between different computers in different parts of an organization, or even from one location to another. For example, we have organizations that have different locations. So computer networking facilitates that. That means then that if you have a GIS department in one location, departments belonging to that organization in different locations can tap into those resources. We have people, and then we have procedures or institutional arrangements that detail and guide how the data is to be used and who is to access it. So let's get into just a bit more detail. When we talk about hardware, we're talking about some of the things that we are most accustomed to with regards to computer hardware. So for GIS, you have to ensure that your computer hardware has sufficient storage capacity and processing power, because because GIS software deals with data of a graphic nature. It consumes a large amount of storage space and processing power. You want to make sure that you have good quality, high resolution color graphic screen, and you have devices for input of the data, such as your keyboard, scanner. For output, you would have your plotter, printers, etc. Alright, now when it comes to hardware specifications, if you are looking to purchase GIS software, for example the ArcGIS, all you need to do is go to the Esri site and search for the specifications of the software. Most software would often tell you what kind of hardware specifications you need in order to run the software. Then the software itself must provide certain types of tools to facilitate input, storage, analysis, transformation, display, and dissemination of your data. So essentially what you're looking for in the software is that it must have essentially 5 major functions. Okay, as mentioned before, it must have functions where you can input data and also correct errors. That's the verification here. The software must allow you to be able to store and organize your data. That's organization, is the data management. This software must allow you to make transformations to your data. Remember, in the last lesson we talked about transformation. So transformation means change the data. Those changes can be in a multitude of ways. It can be to change your file formats. For example, when we talk about file format change, you might talk about things like maybe the ability to export your map as an image in order to insert it in a report. You can transform your data from one coordinate system to another. Those are examples of data transformation. Your software must also allow you to prepare data for output, such as map layouts and presentations. Okay, even those export images of your maps would come into this category as well. And finally, your software must be user friendly to allow ease of use and interaction by your users. So it must not be so complicated that people have to be trained in order to use it. This here is just a schematic of the functional groups that we just talked about. Here again, data input, organization in your database, transformation, display, and user interface. So all of that should be familiar to you. So I won't stay there. So with regards to the functional group, information, the data input and verification, So in a practical sense, what does that mean? So your data sources, for example, these are examples of data sources. You may have paper maps, aerial photos, sensors or data from sensors such as maybe radio waves or satellite imagery, as well as field observations. When you go out onto the field, you log your information that you've collected to and attach it to an XY location. So those will be field observations. Once you collect your data sources, you need devices in order to put it into your GIS database. For example, you can type it in on your computer keyboard. You can use digitizers. We will get in one of the later lessons, we get a little bit more into digitizers. So in this case, in the GIS context, a digitizer may be a tablet digitizer where you can attach your paper map to this electronic table, and there is a little device that looks like a mouse, a computer mouse, that allows you to trace the features on the paper map, and that is then connected to your computer screen, where as you trace, you have a digital representation of what you're tracing. A stereo plotter would be like a very large printer that can print maps. Of course, most of us are familiar with desktop scanners. That is another device that can be used for data input. You also have very large industrialized size scanners that you will often find in government offices and places that produce a lot of data. Those are very large and also very expensive pieces of equipment, so that those can scan large paper maps. All right. I don't know how much we're really into the magnetic and optical media anymore, but these are some examples of the devices that you would need for input. Data storage. Right. So data storage, your software must facilitate storage, as I said. So not only input, as we talked about in the previous slide, but storage, where it helps facilitates organizing the data into a specific way that is required by GIS in order to carry out all those functions. The database component of it as well allows for you to perform queries and retrieve certain subsets of data. So when your software is organized like that, we call it a database management system. Okay. Note that GIS software addresses the way in which information about a geographic feature are related to each other. That spatial relationship is what we refer to as topology, not topography. Please be clear about that distinction. The word looks similar, but they are spelled differently and they mean something different. So spatial relationships, the word we use in GIS to describe that is topology. So a GIS software database management system will organize your data in such a way that it helps to describe spatial relationships or topology. Data transformation, we mentioned that before. Transformation, for example, could also mean the removal of errors from the data. In other words, correction of errors. So your software should be able to facilitate that. For example, the identification of errors, whether the errors are in your tables or on your map, and also the correction of it. So this is another definition here of transformation. Okay. Transformation can also mean applying a large array of analysis methods to the data to achieve an answer. So the answer or the final result means your data has been converted from one state into another. So that's also another example of transformation, right? So that is what this diagram here is highlighting. Correction, maintenance and correction of your data, updating your data, or analysis and utilization of your data to produce new information or new answers. And then we have output and presentation. So the way the data is displayed and how the results on analysis are reported, maps and presented in tables or figures. So these are the types of output that you can have for presentation. What are some of the devices or equipment that can be used to facilitate this or to produce that output? The computer screen will display your final map. Printers can actually print out those final maps so you can have a hard copy. The final paper map or plotter, paper or film plotter. And then again here we have some older technology that's not much in use. So what is the final product? So note, this is the equipment or the devices used to facilitate output and presentation, and the actual output or the product would be the maps, whether the maps are in a digital form or paper form, tables, graphs, or videos. Alright. Now in the case of videos, can be integrated into GIS by creating hyperlinks to features on your map. So you all may have seen some of these somewhere before. For example, if you are looking at a map in a digital environment, all you do is you place your cursor on the particular feature. Let's say it's a point feature, let's say a water well. If you click with your mouse on that particular feature, you may be able to pull up other information about that map, about that feature. It may be documents, it may be videos, etc. People. We need people at every stage of the geographic information system. We need people to plan. We need people to implement and also to carry out the operations. People would need to be involved in planning for the GIS development, identifying the data that is needed, collecting the data, integrating and inputting the data into the GIS system, using the data, performing the analysis, and preparing the output. So people are critical to every part of this geographic information system. Okay. So what is the importance of GIS? What is so useful about GIS? This is the question we want to answer now. So when we look around what's happening in the world today, we know that we have exponential population growth happening globally, and this has been something we've been dealing with probably since the Industrial Revolution. We have technological advances that are occurring at the same time, and what is happening is all of these phenomena are putting a strain on the natural resources and the consumption of our natural resources. Now remember, our natural resources are finite. It doesn't grow, but yet we have population increase and we have technological advances that are consuming these resources. So what do? We must wisely manage what resources we have in order to meet the needs of our population, because remember, human beings can't exist without consuming resources. This means then that wise and proper management of those resources, we need information and we need understanding of the information that we have, and GIS helps to provide that tool and that resource that is required to make better decisions with regards to how we manage our resources. So we have, as I said, we have problems in the way that we manage our resources. So what you find is that for example, most suitable lands had been inhabited due to urbanization and population growth. All right. but we still need food, we still need resources. So how do we manage these things? We need information, and we need in particular geographic information. So what would the GIS help us to do? It will help us to determine where the problem occurs, that's location, and help us to determine who is affected by those problems, so who is impacted. So we're talking about impact analysis now. GIS mapping will help us able to identify impact areas. GIS helps us to identify a point of origin. Let's say, for example, this is very useful for pollution. Pollution often has a point of origin, such as, let's say, an oil spill or a chemical spill. Helps us to identify, again, as we said, the location of the problem and the extent of the adverse environmental or socio-economic impact. So notice here we not only have the environmental impact that we're able to map, but we're also able to place socio-economic information on our maps as well. So once we have that information, what do we do with it? GIS helps in devising practical plans, right? So the GIS can help us with the planning now that we have the information and we have some understanding of what our situation is. So GIS can help us monitor the situation. Remember, we map information about geographic features at a particular time and location, right? So GIS can help us monitor that information. GIS can help us manage it. For example, GIS can help us design buffers or exclusion or inclusion boundaries, either to permit certain types of, let's say, land use activity within an area, or to exclude it if it is appropriate. GIS can help us plan for mitigating damage. For example, GIS will help us identify areas that are prone to landslide or flooding, and as a result we'd be able to flag those areas for some type of let's say rehabilitation engineering work to minimize the possibility of landslides or flooding. GIS can help us provide efficiency in delivery of goods and services, identify shortest route from point A to point B. So we're not only talking about delivery of goods and services in the sense of let's say business operations, but this particular type of principle here can also apply to, let's say, police response to emergency calls or fire services, etc. Here we have an example of how GIS can be used for monitoring. Now these here are examples of satellite imagery over where are we here? King County in Washington State, I believe, in the US. Alright, now this here is an image from 1936 and this here is an image from 1996. How do we know it's the same location? You can look for common features. So for example, if you look at what I believe these are roads, alright, if you look at the configuration of those roads, you can see that it actually still exists here. So this first one, if you followed my cursor, you can see that. Then you see, right, so we can see the roads here. But what is the distinct difference? You can see a distinct acceleration in urbanization. And how do we know it's urbanization as well? If you look at the well organized gridded pattern, we see a lot of man-made landscapes in this photo here compared to this one. Alright, so that's an example of monitoring. On change monitoring, our landscape has changed. GIS can be used in crime mapping. So we see we have some mapping methods here to represent data about school kids and drug arrests. So we're looking to see if there's any relationship between where the school kids are and where the drug arrests occur. Alright, if we look at our legend here, we see that the circles represent the number of school children per household, apartment or house. The larger circles represent larger numbers of students. And then the graded colors, this is density mapping, represent the density, or in other words, the numbers of drug arrests. So the yellow is less, the brown is higher. Alright, so we overlay the two sets of information on each other, and we should be able to determine relationships. So for example, we see we have some hot spots here. We have large circles overlaid on top of some dense areas. So this seems to be a problem area here. We also seem to have a bit of a problem area here. And this type of information now can be used by the police service to plan their crime management strategies. Maybe they can use this information to determine, all right, we need to put some police posts here and here, we need to do some community work in these two areas, etc. All right, so that's where the planning comes in. So we have monitoring and planning. Here we have another type of GIS mapping that can be very useful. We call this hybrid mapping. So two sets of information. We have administrative boundaries and emergency facilities. Now I know we can't really see the details on the legend here, but really what I want to highlight to you is just the type of visualization where we have raster and vector data representations used for improved visualization. What do we mean by raster? We talk more about raster and vector in upcoming lessons. Raster, for example, would be the satellite imagery picture that we're seeing underneath, and on top of that the vector would be like these colored features that we're seeing here. But note there is a bit of transparency there so that we can still see the details of the features underneath. Because oftentimes when you look at a satellite imagery, there's so much information and data going on that you can't really clearly identify anything. But then when you overlay the vector, which is the colors on top of it, each of the colors represent different features. So for example, this looks like maybe a sporting complex. We can see where the boundaries are. So it means then that we can actually have better visualization and understanding of what the data is showing when we use this method by overlaying one type of data over another type of data. Alright, we actually have a brief introduction to our raster and data models here. So in GIS, we have two basic types of spatial data that represent the real world. In other words, we represent the real world in two forms. We can represent it in raster and vector. So each of these visual representations represent the same location, but they represent the data differently. This is our raster, this is our this is our vector here, and this is our raster. Now in the raster data model, the land cover is represented by single square cells. You can see the gridded pattern there. Each cell will have a numeric value corresponding to its land cover. So those in this case you can't see the number, but what is occurring is the numbers are actually being displayed by colors. So everywhere you see blue is a particular number, and here it represents water bodies. So you have rivers, you have I think it's a lake here. The green represents forests, and the yellow I believe is marshland. Okay, whereas in the vector you find it's represented by area features, alright, and lines. So if we go to the next slide, you see the description of what I was talking about. Okay, with the vector model, so this is the vector representation. The features on the earth are represented by the points. Well, this example doesn't have any points. We have lines, which are our rivers and streams. Routes are something different. Routes, for example, might be pipelines and roads that, in addition to being a line, it also has flow direction. For example, a road, traffic would flow in a particular direction. Water lines, the water would flow in a particular direction. Then we also have the polygons. So for example, the marsh, forest, and the lakes are polygons. A region is a type of polygon, but it is a polygon within a polygon. For example, our lake is a region, because we see the lake is inside the marsh. The thin triangulated irregular network, this is an example. This is really a vector method of representing surfaces. So surfaces are different from points, lines, and polygons. Surfaces will, in this case, it's representing landscape. So you see the little triangles, they all fit together like a puzzle to make a surface. So what are the advantages of the raster data? The raster data represents continuous data, meaning there's no break in the information. For example, on your map, every point on your map where you have those cells gives a measurement of slope or elevation or even chemical concentration. Imagine if you have a chemical spill in the water that diffuses and spreads from your point of origin. What we're saying is, if you use the raster data representation, you don't have any breaks in the information about your chemical concentration, right? You don't have a sudden disruption in information across that space. Okay, the raster data represents multiple features. So as you have seen before, you can find points, lines, and polygon features on a single raster data layer. Note that in the vector representation, you would separate those types of information into layers, and then you can overlay them on each other. Additionally, with your raster data, you can have rapid computation, because remember, these cells, the values in the cells would be numeric, so you can do quick mathematical operations within a layer or between layers. This is why we refer to that type of analysis with raster data. We refer to it as map algebra. What are the advantages of our vector data? The vector data represents true shape of the feature, size, and location better than the raster. Alright, because remember, for example, if you have a point feature that occurs within a cell, that cell will represent a specific defined area. For example, it might be 1 square meter. But if your point feature is much smaller than that 5 square meters, right? You can only assign one value to that 5 square meters, and yet your point falls in there somewhere. So you can't identify precise location. All you know is that that point feature falls within that 5 square meter cell. Alright, similarly for the shape, where are the boundaries of your let's say a polygon feature? Where are the boundaries? It's hard for you to tell precisely where the boundaries are, because an entire area has been assigned the value of the boundary of your let's say a lake, right? The entire feature. Hence the reason you find it would be jagged edges with the vector, with the raster, just as we had seen here. If you look at the vector, we see nice clean boundaries here, whereas with the lake in this raster, the boundaries are jagged. Look also at your rivers. Alright, if you have a river line flowing through there, it's difficult to represent it nice and clean as in the vector, because you have to assign an entire value, or assign a value to the entire cell. So let's go back to where we were. Oh, right. The vector also represents non-continuous or discrete data such as the rivers, political boundaries, road lines. It represents it best. Alright. You also have sudden heartbreaks in information. Unlike the continuous data, of course, you have to determine which features would be best represented here that does not require continuous information. The vector also creates more aesthetically pleasing maps. I think for most of us, our human reaction tend to be more drawn towards the cleaner lines than those jagged lines and boundaries for the raster. And additionally, the vector, it takes up a lot less space on your storage devices, because raster datasets tend to consume a lot of storage space. Alright, so does the vector to some extent, but it's more so than for the raster than the vector. Alright, now this is just again another representation side by side of the raster versus the vector, showing the same data. So that's just a visual for you there. And here we have a number of different layers. The features that represent each of the layers and the type of file, whether it's the file type, whether it's point, line, region, polygon, etc. So wells would typically be points, streets would typically be lines, land use, polygon. These polygons are our area features. A lake, as we had seen before, might be defined as a region because it is a polygon within a region. Bus route, remember, a route is a line, but it's a line that contains flow information, so we call it a route. Soils may be raster if you want continuous unbroken information, but you can also choose that if you want to generalize your information, you can choose to represent it as vector as well. But remember, with the vector, the boundaries between one soil type and another is a sudden change in information. It's not gradual. But remember, in reality, change from one soil type to another would tend to be transitional. Okay, so if you want accuracy, you use raster. If you want generalization for the soils, you can use vector. And then elevation, we can use our tin as we looked at before. What are some of our sources of spatial data? So we just look at this briefly. In another lesson we look at, later on we look at it in more detail. So spatial or location information can be retrieved from census and survey data. What are our census data? For example, census data might be population census data. Typically, we find that we will get spatial or location information contained within our census data because there would be address information. Now, address information would not be a precise XY location. It would approximate the location, but GIS can accommodate for that. Our survey data, well, yes, the census and survey data would typically be the same type of data we're talking about, such as questionnaire surveys. We get information from our aerial photos as well. Aerial photos are those photos that we get of the Earth's landscape that would be captured from planes that fly the length and breadth of the country overhead at a certain elevation with the cameras mounted on it. And these aerial photos can actually provide background data for GIS or base information where you can overlay other information types on it. This was the first method of remote sensing. Remote sensing being the process of collecting information about the Earth's surface from above without being in physical contact with it. So this is your definition here. Aerial photos is also a relatively inexpensive source of image information for GIS. Then we have our satellite imagery that can be collected by the sensors on board the satellite. So the distinction between the aerial photos and the satellite imagery, one of the distinctions is that the fact that The satellite imagery is captured at a much further distance over the Earth's surface, and usually the geographic coverage of the data would be much larger as well. What are the advantages of this method? It provides information in a digital format automatically, whereas with the aerial photos, oftentimes you get those aerial photos in hard copy form and you have to convert it. Additionally, with the satellite imagery, you can capture data in different wave bands or different electrical energy signatures, and each of those energy signatures will give you different information. For example, you can get information about water on one wave band, about vegetation on another wave band, and as mentioned before, you get larger geographic coverage, and additionally you have the benefit of the repeat coverage because you have our satellites orbiting the Earth over various predetermined period, so we can have continuous monitoring of our landscape. Information can also be collected from surveying. This is a different type of surveying than we talked about a few slides back. This is engineering surveying, where surveying is data is collected using manual techniques. I shouldn't say manual techniques, but you have to go out onto the field, because modern digital surveying allows you to go out there with some high-tech equipment now, such as total stations, that's what we call it, that allows you to capture information about distance, angles, heights, etc. at a particular location, and automatically log it and upload into your system. Alright, you would often see some of those guys out there when they go out into the field with their yellow tripods and some instruments or equipment mounted on top of it. And then we have our GPS equipment, global positioning systems, where the GPS also works by satellite communication as well, where your handheld equipment, for example, will store coordinates or XY locations, as well as associated attribute information that can be downloaded or uploaded directly into your GIS database from the field. Alright, we also have another source of information, which is LiDAR, light detection and ranging. LiDAR, this uses light in the form of pulsed laser to measure ranges. So in other words, your device, usually on a plane or helicopter flying overhead, it will send out these pulses to bounce off the Earth's surface, and it would measure the speed of transfer of those pulses back to the sensors, and that information is used to derive and develop a digital surface. So for example, you have two types of LiDAR information that you can get. It can be used to derive topography, meaning landscape above water, or bathymetry, which is landscape below sea level. So for oceanography and those types of studies, they might use that type of information, bathymetry. LiDAR is usually considered to be very precise and accurate. Okay, so what are the capabilities of GIS? We've been talking about some of this. Location analysis. GIS shows relationships between a feature and other phenomena. Example, GIS analysis may show the connection between burglary incidents and household income. So we may have two separate layers: burglary incident one layer, household income. If we overlay them, wherever they meet, we find a relationship. Wherever those data layers intersect, we will find a relationship. GIS can help satisfy spatial conditions. For example, locating a police station based on certain station sighting criteria. So we were looking at some crime mapping maps before, and we might, based on what we're seeing, we can run a query and say, well, you know, if more than a certain type of number of incidents of crime, burglary, occur within this specific area, and it is beyond a certain distance from a police station, well, now we will have to place a police station there. So that is the kind of scenario we're talking about. Then there's temporal analysis, as in time. For example, land use have changed dramatically over the years. Thus, by storing and comparing maps of various dates, GIS can perform temporary analysis or change monitoring. We can also have GIS being used to evaluate different scenarios. Those scenarios or simulations with what we call modeling. What would happen if? This allows the user to construct a hypothetical situation and forecast the outcome if certain hypothetical situations exist. So this type of modeling here in GIS is actually a very important planning tool. And little later on in the course, hopefully we would get to look at a particular case to see how this type of modeling is done. Okay? At this point, I would like to thank you for joining me for today's lesson. Please refer to eClassroom for the activity for this week. Thank you.